got a lot of stuff here. I guess I'm going to call today tidying up loose ends day, and you know, putting things together. Chapter 11 is our main goal for this week. It breaks into 3 sections. When you do the homework, I've broken into 3. We've covered a lot of this, but I want to kind of make sure that all the loose ends are taken care of. And the first thing is, the first one of them is called Estimating a Single Mean Without Salt. Its full title is Chapter 11. And the second one is Doing It With Salt. We already know that as well. And then the third one is calculating the difference between means with salt. So we're not even going to do it without in that case. So let's just tidy up all the little loose ends. Right, suppose you wanted to estimate using a confidence interval a single mean, but you wanted to do it by hand, by calculation. Well, there are 2 ways to do that. For any sample X bar of size n and a standard deviation of this guy, you can find the confidence interval using the empirical method, which generates those confidence intervals. And that's questions 5 and 6. Or you can use the general method, which is this one. Right. Can you remember empirical method? The mean plus or minus 1 standard deviation, 2 standard deviations, 3 standard deviations. Right. And that gets you a 68, a 95, and a 99% confidence interval. A slightly more efficient version of that one would be this one here, the general formula. In that case, 90% is 1.645, 95% is 1.96. My puppy was coughing there, I was just worried what she was up to. And then a 99%. So you got these written down on a card somewhere, you just pull them out and you put them together. X bar obviously is the mean of the sample. We use letter n to mean the sample size. And the standard error is the standard deviation divided by the square of n. So you would typically be told these 3 guys, and then you'd be asked to do this one and this one. Now I'm telling you right now which of there's only 8 questions in this, but which ones are used. If they see the word empirical rule, or you see 68, 95, 99, and there we go, 99.7, you know you're using this. If you don't see that phrase or these, and you're just asked for one of them, then you'll assume it's a general one, which is only question 8, and that would be it. Are we comfortable with all those guys? You're used to the formulas? Do you want to see an example of each, or can we move on? And that's why I have video or whatever. Okay, we can do it the thumbs up. If you want to see a question, say stick a thumbs up. Want to see one? Okay. So let's suppose we do an empirical rule. You work for a company that makes bags of, I don't know, cornflakes. They're meant to be £1 bags. So you want to check that out. You get a sample of size 10 and the average weight of them is 16.2 ounces. And the standard deviation was 0.2 ounces. And what we want to do is find a 90% confidence interval based on this data. And let's say that they wanted you to do it using empirical rule. Well, that means you're using this one. So your 95% confidence interval is X bar plus or minus 2 standard errors. This guy is 16.2 plus or minus 2 times, and the standard error is given by this formula down here. So all you need to do is take the standard deviation, which is this guy, and divide it by the square root of the sample size. So do that on the calculator. It's going to be 2 times 0.2 divided by the square root of 10. Sorry about that. Yeah, it's not a very good breathing day today. 0.13 to 2 decimal places. And we call this number here, I'm not going to ask you now because I'm sure you've heard me say it tons of times. This is called the margin of error. So let's see what our interval looks like. You take this away from that, you get 16.07. You add it to this, you get 16.33. So we are, I just said 90. Better make sure I'm consistent. We are 95% confident that the average weight being produced by this machine is somewhere in that region. Now, if that was the case, you would be okay with this machine. And why are we okay with it? Well, it's meant to produce 16 ounces. And this one is guaranteed. Would you agree? All these numbers are greater than 16 ounces. So that is okay. Weights and measures, government regulations say that if you tell us that that box has a pound of potatoes in it or a pound of flour in it or whatever else, cornflakes, it has to have that, right, as an average. You can't produce things where, well, you might get 14 ounces, but you might get 18 ounces, right? That's just too inconsistent. So that would be counted as definitely okay. You could say with fair degree of certainty that there's more than 16 ounces in a typical bag. Okay. And that would be an example of using the empirical rule. Now, the only real difference between this formula and that one would be this number here. Can you see on the 95, it's 2. But if you're using the more accurate, the general formula, wouldn't you change that just to 1.96? So there's only a minor difference between the two formulas, and it's all to do with what you use as the constant here, what number is used. Are we cool with that? Any more questions? Okay. Next one on my list. That's the first one in chapter 11 kind of covered. I think there's 8 questions in it. This is the next one, and it is, how do you do it with salt? And we did tons of those guys. I'm just going to do one, just as a kind of example of how that works. If you can bear with me for a second. I'll look it up. Here we go. It's called Chapter 11, Estimating a Single Mean Using Salt. Here it is. All right. Something I need to do here. Close the wrong window. Golly, I've got a stupid thing coming out and popping up in front of me. Okay, let's try that again. Third time lucky coming up. Right, so take you through an example using salt. Here we go. you're told the mean, standard deviation, and the sample size, and your job is to create a 95% confidence interval. So I'll just hit use salt. And we go into salt here, and we have lots of choices. Picking one sample T. And the mean, oh, let's say the mean was 75. Let's say the standard deviation was, say, 12. Let's say the sample size was 11, right? So you just put in whatever the mean, the sample deviation, and the sample size is. You go down here, and you hit confidence interval, and you put in whatever number you wanted, say 95, and you generate results. And here would be your interval. Roughly, what, 66.9 to 83.1. So if you want to use salt to generate any kind of confidence interval, you just make sure that you're on the one sample T. The one sample T is used because you don't really know your data is normal, and your samples might not be very big, and this T distribution can cope with those situations. Now, it's much better if the sample size is huge or bigger, because when you do that, you see how the intervals change. And if it's really big, like over 1,000 is really big, can you see that the difference between the small and the big now is only about 1 unit? So when your sample size was tiny, you had like a range of, what's that, 14, 17 units. And when your sample size is huge, it only does 1. In fact, let's be silly, if you had 11,000 things in your sample, can you see that you're pretty sure within a unit, right, about, well, actually half a unit, where the right answer is. So as you increase sample size, what you do is you're shrinking the confidence interval down to a point where you're pretty much going to guarantee that you know the answer to what the mean is. Are we good with that one? Do you want to see another example of using salt to get a 95 or a 99? Or are we good with that? Any feedback would be helpful. We could do the thumbs up if you like it. If you're okay moving on, the thumbs up. That's what I need. Okay. Last chance. If you're not happy, thank you, Jessica. We are good. Won't it be fun once we're back in class and I'll just look at your faces? I'll know if you're happy or not. But until then, I kind of need to pester you a little bit. Okay, so we're now moving on to estimating the difference between means with salt. Now, the only way we're going to do these guys is with salt, right? So we're going to use software. But I want to at least make a little bit of an attempt to give you an idea of what the calculation is looking like inside the machine, right, inside the software. So what you have in this case is you're going to have the classic 2 populations. So in this side, we're going to have males, and this side self-identified females. And N1 is the size of this sample. I'm making it 100. N2, I'm going to make it 120. In this one here, we measured their average height, and it was 69 inches. And here we measured the average height, and it was 67 inches. And so a question that might be asked is there enough evidence to prove that males are taller than females? It's not probably the most interesting result about people, but superficially, would you agree it looks that that's the case? But how do we prove it? And the way we prove it is we have to combine the data in some way. And the typical way of doing it is that we find an estimate for the difference in the population means, right? We're not interested in, are these samples bigger than the other? Because that's obvious, right? That one's 69, that's 67, right? What we're more interested in is, if you use this to represent all males, and if you use this sample to represent all females, is there enough evidence to prove that the mean of the populations, remember mu1 and mu2, is that positive, isn't it? Wouldn't that mean males are taller than females? There is a formula for it. We could do an empirical one, but we won't. Let's do a general one, because actually the general one is closer to what's happening inside the computer. So for instance, a 95% confidence interval for the difference between the two means is given by this formula. X1 bar take away X2 bar, plus or minus. Anybody want to have a guess at what fixed unchanging number goes here for a 95% confidence?
1.96.
Isn't it the same number when it's population proportions as well? Right? That one, that's a fixed value, times the standard error of X1 bar take away X2 bar. Now, the formula for getting the standard error of the difference is the square root of S1. Oh, I forgot to tell you. S1 is 5, S2 is 4, right? Is S1 squared over N1 plus S2 squared over N2. I think after we've done one of these by hand, you'll be glad why we use, solve. Now, S1 is standard deviation of the males squared divided by the sample size of the males plus S2 over N2. Now, there are two kinds of standard error formula. One of them is called pooled sample. And the other one is an unpooled sample. This particular one that we're using is the much more common one, which is the one I'm showing you, is an unpooled sample. What you're assuming here is that the two populations are quite distinctly different and that their standard deviations, therefore, are likely to be different. So you use unpooled when you believe that the two populations are different and that their standard deviations are likely to be different. If you had two populations, but you believed that their shapes were similar and that their standard deviations were the same, then you would do a thing called a pooled sample. And I'm not sure the formula, it's pretty obvious. But essentially what you do is you take all of the data and you stick it into one massive set of data, and it's the standard deviation of that combined data that you use. It's kind of like that, not very pretty. So if you take this guy, which is 5 squared, and you divide it by the sample size, which is 100, and then you take the next one, which is 4 squared, and you divide it by a sample size of 120, that's what the standard error would look like. Okay, let's put that package together then. 69 take away 67 plus or minus 1.96 times that guy. 5 squared over 100 plus 4 squared over 120. Right, I'm about to do this on the calculator. Do you think there's a big enough difference between these two for this 95% confidence interval to contain nothing but positive numbers? Because that means the first thing is bigger than the second. Do you think they're far enough apart for that to happen? Or do you think that, nah, they're just too close? Any gut feelings? Okay, hopefully you got that idea. Let's see if you're right. My gut feeling is that they're not going to be, but I get these wrong all the time. So 2 plus or minus 1.96 times square root, first guy divided by 100 plus second guy divided by 120. And the answer I get is plus or minus 1.21. So we are going to have 0.79 all the way up to 3.21. And guess what? I was wrong. This 95% confidence interval for the difference between the two means isn't all positive. And if all the numbers in the interval are positive, that means that the first one is bigger than the second, right? Males are taller than females. What would it look like if I had this? Right, they're all negative. What would an interval where all the numbers in the interval are negative tell you about these two fellas?
M1 is less than M2?
Isn't that exactly the same way you interpret the proportion one? Remember the P1 take away P2 guys? Right, so there's a lot of similarity going on here. Now, for completeness sake, can you also get an interval that looks like that? And that we call something like it contains 0. What, if any, conclusion can you make when the interval for the difference contains negative and positive values as it does here?
Inconclusive, right?
Yes, inconclusive. If you've got a test question like that, if you can't remember the word inconclusive, put a phrase that means the same, something like, there's not enough evidence to tell, right? Or we don't know, or you know, something along those lines would be just the same as saying inconclusive. Now, if you look at this, it's not a horrendous amount of work, but would you agree it would get pretty boring pretty quickly if you had to do a lot of them? So wouldn't it be nice if we could get all of this to be done using salt? And that's exactly what we're going to do. I think I got the thing set up now. Just loading it up. Trying to find one along those lines. Not easy when you, come on, where are you? Okay, let's take, this is question 10. I'm sure I can find better ones if I spent more time, but first one that I could see that was similar to that. Okay. Make it a little bit bigger, hopefully. See what the story says. Volunteers who had developed a cold within the previous 24 hours were randomized to take either zinc or placebo lozenges every 2 to 3 hours until their cold was gone. So if you've ever had a cold, do you know that you can get those? Zinc is allegedly helps the immune system. In other words, it helps you recover from the flu, from the cold, things like that. And this is us doing an experiment to see if there's any evidence to prove that. So can you imagine, well, a lot of these are actually done in universities. University students get used a lot because they're a good source of people who need money. So you have these posters all over the place saying, have you got the cold? Or something like, would you like to earn money? And then they say, okay, if you've just got the cold, contact us right away. And you get paid, whatever it is, $50. And in this particular one group gets the real zinc, right? The zinc lozenges, takes them with a cold. And the other lot just gets a bit of candy that looks just like a zinc lozenge, right? There's no difference, you can't tell. So it's probably a double blind going on here. And 25 people took the zinc one. So I'm writing these numbers down because you need to know them. So I'm going to have group 1, I'm going to call them the zinc. And group 2, we're going to call them the control. The control are the ones that don't get anything pharmaceutical. The zinc one is N1, and that's 25 participants, which I got from here. And 23 took the placebo. So that's the other group. For the placebo group, the mean overall symptoms was 7.2 days. Well, that's a long time to have a cold. And the standard deviation for them was 1.4. So are you comfortable with how if you get used to the notation, right? That's where those numbers. Now the mean overall for the other group was 4.9 days. That can't be right. I got that totally wrong, but I can fix it by just calling them switching places. So that's okay, I fixed it. So evidently, the placebo group's going to be called 1, and the people who are getting the zinc are called 2. So it's the same numbers, I'm just calling them, switching their jobs. So X1 is this guy, S1 is that guy, sample size is 23. That was annoying. Do you notice how they said it one way and then they switched the data later, which is what got me. And if you take the other group, 4.9. So that makes more sense. And they are 4.9 and it's 1.4 as well. So first one, calculate the difference in the sample means. So if you take 7.2 and you take away the other one, which was 4.9, you would get that the difference between these was 2.3. So it looks like if you take zinc, it'll knock 2.3 days off your recovery, right? In other words, you'll get better quicker. Now, the standard error, well, I don't need to. Let's use salt to do it. I mean, do you know that horrible formula I had? I could do that by hand, couldn't I? Do all that square root stuff. I'm going to go in here and use salt. There we go. And 2 samples. Sample 1 is going to be 7.2. The standard deviation was 1.4. And the sample size was 25. And the second one, the ones that did get the zinc, well, they had a mean of only 4.9. And the sample for that was 1.4. And the sample size in this case was 23. And we are doing a confidence interval. And now we have to decide, is this a pooled or an unpooled one? Now, I believe that the picture is gone and I won't be able to get it back unless I go somewhere else. Here we go. That they said somewhere, I'm looking for it. Do you see any indication of them being pooled here?
Yeah, it says compute the unpooled standard.
There we go. You see that there? Somewhere or other, they got to tell you, right? And it says that they decided to do unpooled. So, okay, unpooled it is. If you click on that box, it's called assumed equal variance. You see that one there? Leave it blank when it's unpooled and check on it when it's pooled, right? So if you know it's pooled, hit that little guy. I wish that just said pooled, right? And you could just hit it, right? But it doesn't, right? So unpooled, leave it alone. And now you generate your results. And the guy that you're interested in is this set of numbers here. And I'll write that down. It's 1.49 up to 3.11. And we have finished our first. Difference between two means. Okay, let's interpret that now. The average number of days, right, between the two is positive 1.4 to positive 3.1, right? So when you get the zinc and the nut thing, right, these are the no zinc, and these are the zinc, right? Since these are all positive, doesn't that mean that this one is bigger than that one? Agreed? Now, mu1 are the people with no zinc, and these are the ones who did get zinc. So I would interpret that kind of weird way. If you don't take zinc, isn't your cold going to last somewhere between 1.5 and 3 days longer? That makes sense to say it that way. My brain would want to say it the other way. If you take zinc, won't your cold last 1.5 to 3 days less, right? It's the same thing, back to front. And that you could then do as part of your advertising campaign. If you've got a cold, take our super duper zinc lozenges. We have done, double blind experiment, and it has been shown that they reduce the length of your cold. Well, you might not want to say this. You might say by on average 2 days. You might fudge it a little bit, right? Because doesn't it sound better on average 2 days rather than say somewhere between 1 and 3 days? I think that would probably work. And that would be basically the strategy. So let's try, one last one for today. Let's do a classic clinical trial, and we'll do it the way I would choose to do it. And so we have a new drug, and we have the old drug. This is the control. This is the experimental group. This is the control group. And as always, these stories tend to be the same. Is there any evidence to prove that the new drug's doing a better job than the old drug, right? So let's assume that this drug, its job is to reduce your blood pressure, right? Right? So your blood pressure's too high, it's meant to reduce it. And you collect data from each of these two groups. You collect data on what it was like before treatment, and then you give them 4 weeks of this treatment, and then you measure their blood pressure. And in this group here, there was 200 volunteers, and that the blood pressure was reduced by, on average, 15 units. And the standard deviation of this group was 10. And we took this one here, and that's basically the old group, and there's 150 in that. And if you took this medication, your blood pressure did go down. It would go down by 8, and the standard deviation would be 2. Now, before we start doing any kind of salt on that, let's look at some of the other things that we're getting from this here. This drug here is like a pretty good drug in the sense that, you know, it's reducing things. There's not an awful lot of variation, right? So if you take this drug, won't you probably, your blood pressure will go down by about 8, and not a lot of wiggle room, right? Most people, it's going to be 5, 6, 7, 8, up to 11, right? That kind of range. If you take this drug, the standard deviation is huge. I mean, 5 times larger at least, right? Huge. If you took this drug, and I drew a little picture of what it might look like, let's just suppose it's normal. Right in the middle would be 15, right? And if you go 1, 2, 3 standard deviations, you could reduce it by 25, 35, or even 45. Now, if a drug is really strong, couldn't the drug overdo its job? In other words, it might reduce your blood pressure too much, right? That would be a bad thing. If you go the other way, what are the people over here getting? If they took this drug, what would a -5 actually mean in the context of my story? It would actually mean your blood pressure went up. Like the negative of a negative, right? It's going up. In fact, it could go up as high as 15. So this drug has got an awful lot of variation in it. If you looked at this drug, I'll assume it's normal, it might be 10, 12, or 14, and it could be 6, 4, or 2. Can you see that this drug, at least at the worst case scenario, it's not going to hurt you? I agree, it's going to reduce your blood pressure because you need your blood pressure reduced, but it's going to do it negligible. And even in the top end, that number's not too severe, right? So we are going to be looking at the difference between these to see if there's evidence, and then I'm going to return to this little picture. So let's find out what the confidence interval was. What do you want? A 99 because it's medical, right? Want to be more sure? I will move over to the salt where all the number crunching is going to go. And the experimental group had a mean of 15, a standard deviation of 10, and a sample size of a sample size of 200. The control group, much safer drug in lots of ways, but not as effective, would reduce your blood pressure by 8. The standard deviation was very small in comparison, and the sample size there is 150. We're going to do a confidence interval, and we're leaving that blank as you typically would, unless you're told to pull the data. and we'll generate the results. And the answer that we get is somewhere between 5 and 8. So I'll round that to 5.6 and to 8.4. Let's look at that. All these numbers are positive. That means that the first one is definitely better at reducing the blood pressure of the second one. Agreed? If you only took that into account, wouldn't there be a good argument that that new drug should be used instead of the old drug? Have I convinced you that this new drug is much more dangerous because of the variation in its effect? It could actually increase your blood pressure. Now, you got to think it. This is medication for people who are ill and you really need to get the blood pressure down. Do you want to give them a drug that might do the exact opposite? So that drug would probably fail the FDA. They would look at that and say, the dangers outweigh the risks, but it wouldn't be totally a lost cause. There are lots of drugs that they have in hospitals that are never going to be issued to you through your general practitioner, right? You know, I get blood pressure reduction stuff. I get pills all the time, right? So I get those ones, but I don't get the good super duper ones. This one here might still get used, but it would get used in very extreme circumstances. Somebody comes in with a blood pressure through the roof, like they're about to die because of it, right? Nobody can live with this kind of blood pressure. Can you imagine if you gave them this drug, would it have any real significant effect on their health? Nah, you'd knock it down maybe 12 or 14. Isn't this, you give them it. Now, it could save their life, right? Or it could kill them. But they were about to die anyway, right? If you don't do nothing, they're going to keel over and die, right? Their heart going to burst or whatever. Something major is going to fail on them. So there are emergency use drugs, right? They are typically only used in extreme circumstances where, you know, this fella, whoever this person is going to die. And the normal treatments are just not going to handle it, right? Then you might give them that drug. That's where the really dangerous drugs live, right? And you see why it would do a good job? Of course, it might kill them.